Hello and welcome to this new lecture on compressible flow. In this lecture, we'll consider the effect of the change in the cross-sectional area of the fluid on the properties of an isentropic flow. So to start, we will consider the definition of the stagnation enthalpy, and we said that the stagnation enthalpy, which is H plus V square over 2, will be equal to a constant in the case of an adiabatic flow. And also this is valid in the case of an isentropic flow, because as we said, an isentropic flow is also an adiabatic flow plus reversible. So if we take the derivative of this equation, we will have dH plus VdV will be equal to 0. Now I will go a little bit to thermodynamics and use an important equation from thermodynamics called the TdS equation. And in fact, we'll have this relationship between the differential change in the entropy and the differential change in the enthalpy. So we'll have TdS is equal to dH minus VdP. So here guys, V is the specific volume, and please do not confuse it with the capital letter V, the velocity, okay? And we know that the specific volume is simply the inverse of the density, and it is equal to 1 over rho. Now for an isentropic flow where the entropy is constant, ds will be equal to 0. So you can eliminate this term and you can say that dH will be equal to VdP, or in terms of the density, it will be dP over rho. Now let's replace this dH in this equation here. So we'll replace dH by dP over rho, and we will have dP over rho plus VdV will be equal to 0. And I will divide this equation by V square. So in order to write it in a dimensionless form or in a normalized form, we will have dP over rho V square. So you can see like this rho V square like a term very similar to the dynamic pressure, which is half rho V square. Okay, so we'll have a pressure divided by a pressure, so this is a dimensionless number, plus dV over V will be equal to 0. So we will say that dP over rho V square equal to minus dV over V. So we have obtained a relationship relating the differential change in the pressure dP with the differential change in velocity for an isentropic flow. And you can see this important minus sign. That means that dP and dV will have this opposite relationship. So when dV is positive, dP will be negative. So that means when the velocity increases, for example, the pressure will decrease, and vice versa. So this is the first important equation that we have obtained. And now you will say, okay, we're talking about the effect of the area change, and so far we did not see any term is related to the area. Okay, so far we have seen the relationship between the velocity change and the pressure change for an isentropic flow. Now, to include this area term, we will start from the mass conservation equation. So the mass conservation, we know that mass is conserved. Mass cannot be destroyed, cannot be created. It is always conserved. So for at steady state, the mass flow rate of the fluid m dot is equal to a constant. And the mass flow rate is simply the multiplication of the density rho into the cross-sectional area A. So here we're talking the cross-sectional area perpendicular to the flow direction multiplied by the velocity v equal to constant. Now I will take the derivative of this equation. So we'll have the derivative of rho AV will be equal to 0. So the three terms in fact here are varying, they are not constant. So the density is changing, the cross-sectional area here is changing, and as a result, if we have a change in the cross-sectional area, we will have a change in the velocity. And from this equation here, the change in the velocity is related to the change in the pressure. So in fact, we will have this relationship between all the terms if we combine these two equations, this one here and this one here. Okay, now if we continue, let's differentiate rho AV. So I will take the principle that the derivative of u into v is simply u prime v plus v prime u. So I will take like u is rho and v is simply AV. So we will have AV d rho plus rho dAV equal to 0. So we'll have AV d rho plus rho. So the derivative of AV is AdV plus VdA. So the same principle, u prime v plus v prime u is equal to 0. So if you divide all this equation by rho AV, you will have d rho over rho plus dv over v plus dA over A is equal to 0. So now you have a relationship between the area change, the velocity change, and the density change. So I will say that dA over A now will be equal to minus dV over V minus d rho over rho. So in fact, you can replace minus dV over V by dP over rho V square from this equation. So you will have dA over A is equal to dP over rho V square minus d rho over rho. So let's take dP over rho V square as a common factor. You will have dP over rho V square 1 minus d rho over rho divided by dP over rho V square. So let's simplify the densities here, and we will have d rho over dP over dP over V square. So it's better now to put V square in the numerator and you divide it by dP over d rho. So we'll have now dA over A is equal to dP over rho V square into 1 minus V square over dP over d rho. Now if you remember, if you look carefully in the lecture when we talked about the speed of sound, we have said that the speed of sound c is equal to the square root of dP over d rho. So this term here, dP over d rho, is simply the speed of sound square. So we will have now again v square divided by c square, which is, if you remember, v over c is the Mach number. So v square over c square is simply the Mach number squared. So we can write dA over A will be equal to dP over rho V square into 1 minus the Mach number square. So this is a very important expression relating the change in the area dA with respect to the change in the pressure dP and the Mach number. And also if you want to relate, for example, dA with the change in the velocity dV, you simply replace this dV over rho V square by what? By minus dV over V. So you can also rewrite this expression as dA over A is equal to minus dV over V into 1 minus the Mach number square. So now you will see the effect of the change in the area dA on the change on the velocity dV, and also this is related to the Mach number. And in fact, this term between the two parentheses is a very important term, and the value of the Mach number will affect the relationship between dA and dV. So if you look carefully, for example, if you take the case of subsonic flow when the Mach number is less than 1. So when the Mach number is less than 1, this term here will be a positive value. And now you will have, if for example dA is a positive value, dV should be a negative value since we have this negative sign here. So dA and dV will have an opposite relationship when the Mach number is less than 1. So when the area increases, the velocity will decrease and vice versa. So in the case of subsonic flow. However, if you take the case where the Mach number is greater than 1, so Now 1 minus Mach number square will be a negative value multiplied by this negative sign. This will be positive. So now dA will have the same sign as dV. So if dA is positive, dV will be positive. So in other words, what does this mean? This means that in the case of supersonic flow, when the cross-sectional area increases, the velocity of the fluid will increase and vice versa. Okay, so let's write these conclusions. So first, we will consider subsonic flow. Subsonic flow, meaning the Mach number is less than 1. So when the Mach number is less than 1, we will have 1 minus Mach number squared will be a positive value. So as a result, if, for example, dA is a positive value, dV will be a negative value. Okay, so when the cross-sectional area increases, the velocity will decrease and vice versa. And what will happen to the pressure? The pressure will always have this opposite relationship with the velocity, with the change in velocity. Okay, from this equation, if dP is positive, dV is negative and vice versa. So if dV here is negative, dP will be positive. So we can say from this line here, we can read it like this. dA is positive, meaning when the cross-sectional area of the flow increases. dV is negative, it means that the velocity will decrease. dP is positive, it means that the pressure will increase. So when the cross-sectional area increases, the velocity will decrease and the pressure will increase. Now, if dA is negative, dV will be positive and dP will be opposite to dV always. So dP will be negative. So we can read this line like this. When the cross-sectional area decreases, the velocity will increase and the pressure will decrease. So when we create a restriction in the flow, it meaning we're decreasing the cross-sectional area, the velocity of the fluid will increase and as a result the pressure will decrease. So this is, I guess, it is very close to our experience in everyday life. So we know when we create a restriction, the fluid will accelerate, or when we create a diverging section, for example, or we create an enlargement in the cross-sectional area, the velocity will decrease. Okay, so this is very close to our experience in everyday life. However, if you consider the case of supersonic flow, so supersonic flow, so in this case you will be a little bit surprised and it is counterintuitive. So in the case of supersonic flow, when the Mach number is greater than 1, you will have 1 minus the Mach number squared will be a negative value. And as we said, looking at this equation, if this is negative multiplied by this negative sign, so the multiplication will be positive. So as a result, dA will have the same sign as dV. So if dA is positive, that means dV will be positive, and of course dP will be opposite to dV. dP will be negative. So when we can read it like this: when the cross-sectional area increases, the velocity will increase and the pressure will decrease. So in fact, when you have a supersonic flow, in order to increase the velocity of a supersonic flow, you need to increase the cross-sectional area. Okay? And if you have a restriction in the cross-sectional area, so if dA is negative, we're decreasing the cross-sectional area. As we said, dV will follow dA. So dV will be negative and dP will be positive. So when the cross-sectional area decreases, the velocity will decrease and the pressure will increase. So if you want to decelerate a supersonic flow, in fact, you need to create a restriction in the flow. So you need to decrease the cross-sectional area. So let's now try to illustrate, to do some illustration in order to better understand. So we will take two duct geometries. So let's construct a table. We'll call the first column duct geometry And in the first case, we have subsonic flow when the Mach number is less than 1. And we have another case where we have supersonic flow when the Mach number is greater than 1. So the first duct geometry is a diverging. It's called the diverging duct. And this is the flow direction. So if you follow the flow direction, the cross-sectional area will increase. So here, dA is positive. So this is called a diverging duct. So in the case of subsonic flow, dV will be opposite to dA. So if the cross-sectional area increases, dV will decrease. The velocity will decrease. dV will be a negative value, okay? And dP will be positive, so the pressure will increase. So when we have a deceleration in the flow, we call this as a diffuser. And in fact, this diverging duct in the case of subsonic flow is called a subsonic diffuser. So when you hear the word diffuser, we simply mean that we have deceleration in the flow. So the velocity of the fluid is decreasing, okay? And in the case of supersonic flow, if dA is positive, we said that dV will have the same sign. So dV will be positive and dP will be negative. So when the area increases, the velocity will increase in the case of supersonic flow and the pressure will decrease. So this diverging duct is accelerating a supersonic flow. So in the case of acceleration, we call this geometry a nozzle. So in the case of supersonic flow, we call it a supersonic nozzle. So when we see the word nozzle, we mean acceleration or an increase in the velocity of the fluid. Okay. Now let's take another duct geometry, a converging duct. So we have a restriction in the flow. So this is the flow direction, and you can see that the cross-sectional area is decreasing in the direction of the flow. So dA in this case will be a negative value, and this is called a converging duct. A converging duct. So always for a subsonic flow, dV will have the opposite sign of dA. So if dA is negative, dV will be positive, and we said that dP will be opposite to dV. So if dV is positive, dP is negative. And we read it like this. When the cross-sectional area decreases, the velocity will increase and the pressure will decrease. So this is in the case of subsonic flow. So now since dV is positive, we have acceleration. We call this converging duct, in the case of subsonic flow, we call it a subsonic nozzle. So since we have acceleration or we have an increase in the velocity. However, in the case of supersonic flow, if dA is negative, always we said that dV will have the same sign of dA. So dV will be also negative and dP will be positive. So if dV is negative, that means the velocity of the fluid will decrease. We have deceleration. So this converging duct will act as a diffuser in the case of supersonic flow. So we call it a supersonic diffuser. Okay. So this is a very important conclusion here in this lecture. Maybe because in the case of subsonic flow, you already know this. When the area increases, the velocity will decrease and vice versa. However, in the case of supersonic flow, as we said, this is counterintuitive. And if you have a diverging duct, the fluid will accelerate. So when the cross-sectional area increases, the velocity will increase in the case of supersonic flow. And also when the cross-sectional area decreases, the velocity will decrease in the case of supersonic flow. So please pay attention to this difference between subsonic and supersonic flow. I will stop this lecture for now, maybe to digest all this information. And in the next lecture, I will talk about a very important geometry called a converging-diverging duct. So a converging-diverging duct, you will see later on, this is a converging duct connected directly with the diverging section. So you have this this geometry which is in series, a converging section connected in series with the diverging section. Okay, so you will see that we use this geometry to accelerate a subsonic flow up all the way to the supersonic conditions. Because here, a diverging section, we are talking about an already existing supersonic flow. So we're saying that the diverging section will accelerate a supersonic flow, but we did not talk about how to get a subsonic flow to supersonic condition, how we can get there. So how we can get from the subsonic flow condition up all the way to the supersonic flow conditions. So to do this, we will need a geometry called the converging-diverging duct. And in fact, we also use this geometry, a converging-diverging duct, to decelerate a supersonic flow to the subsonic flow condition. So it acts in both ways, in acceleration and deceleration. Okay, so let's stop talking now and let's talk more about the converging-diverging duct in the next video.